So what we're going to talk about here is breaking down rational expressions or rational functions, right? So when, in algebra, we learn how to factor, right? And we can express a polynomial function as the product of two linear and quadratic factors, right? So for example, x squared plus 5x plus 6 is a quadratic function, but I can write it in terms of two simpler linear factors, right? Which then multiply to get x squared plus 5x plus 6. Well, we can do something similar to rational functions, but in this case, we write them as the sum of two or more simpler rational functions. Okay? Now, these simpler functions will have real constants as their denominators. As their numerators. And their denominators will be a power of a linear factor. Okay? Or a quadratic factor. So, this process is called decomposing a fraction into two partial fractions. So, take a look here. We have this fraction, and what we've done to this is we've decomposed it into two partial fractions, as you can see right there. All right? And those two fractions, when you add them up, you get the initial one. Okay. So the first one we're actually going to solve is that example right there. Okay? Now, there are three cases we're going to be looking at. Case one is if you have a denominator with linear factors. So, what we do is this. You take your initial fraction, and we're going to rewrite it, but having factored the denominator. And you see how the denominator factors into two linear factors? Okay? Now, we're going to decompose this into some simpler fractions. Count how many factors it has, and you're going to make that many fractions out of them. So this one is going to turn into two fractions. Each one of them gets one of the factors. Let me do a little more, and then I'll take questions. Okay, now, notice the denominators of these two functions, of these two fractions, are linear, right? The degree is 1. What's 1 degree less? What kind of number is it? It's a constant, right? So the numerator is going to have 1 degree less. It means it's just going to be a constant. So for those constants, we put placeholders A and B. Now, what we're going to do is this. We're going to multiply the entire thing by the LCD. Then we're going to solve for A and B. Okay? Right. So the LCD here is x minus 5x plus 4. Multiply the whole thing by that. All right, let's see what cancels. The x minus 5 is here, the x plus 4 is there. So I get x plus 13 is equal to a times x plus 4, don't distribute, plus b, x minus 5. Now what you're going to do is into these factors that, into this equation, you're going to plug in numbers which are going to make one of the factors 0. Okay? So plug in values of x, values for x, which make the parentheses equal to 0. So for example, here, to make the x minus 5 equal to 0, we plug in x equals 5. So let's plug in x equals 5. You're going to plug into the whole thing. So you get 5 plus 13 equal to a times 9 plus b times 0. So you see how the 0 goes away? 9a is equal to 18. So a is equal to 2. Next, plug in something else to make the other factor equal to 0. Now let's plug in x equals negative 4. Negative 4 plus 13 is equal to a times 0 plus b times negative 4 minus 5. Right? So 9 is equal to negative 9b. So b is equal to 1. Yes. Okay, so now we solved for a, we solved for b. Now we're going to rewrite this fraction. My initial fraction was this. X minus 5, x plus 4. So now that's going to equal these two fractions, right? I had an x minus 5 and an x plus 4. So now just look here. The x minus 5 had the a, which is now a 2. The x plus 4 had the b, which is a minus 1, but the way I write it is I put a minus here, 1 there, right? And so that is my answer. Okay, so now, the first thing you're going to ask is, do we have to make the minus like that? And my answer is going to be yes. Don't do plus and minus 1 over because we're elegant, sophisticated math student. The next thing you're getting prepared to ask me is, do we have to rewrite the initial fraction every single time? You know, yes, you do. Okay? All right, any other questions that I didn't anticipate? Okay. Okay, now, still with, a denominator with linear factors, what if you have an improper fraction? Yeah. Yeah. Huh?
Are we going to have like two separate?
No, that's just adding fractions.
Okay.
We've been doing that forever.
Oh,
now we're going this way. Yeah. Okay. An improper fraction is if the numerator has a degree equal to or greater than the denominator. So for example, if you have x squared over x squared or x to the 4 over x cubed, right? What we're going to do is this. You need to use long division to rewrite the fraction as quotient plus remainder over divisor. Now, you need to decompose this one. Okay? That's the one you need to do partial fraction decomposition on. So, let's do this next one then. Notice how here you have an improper fraction. Now, you're not going to be told, hey, this is an improper fraction, so no, you have to figure it out on your own. This is an improper fraction because the numerator has a degree equal to or higher than the denominator. So first, we do long division. All right, so here we go. X squared minus x, negative 2x squared plus 9x minus 4. Divide first term by first term, you get negative 2. And we get negative 2x squared plus 2x. Now, change the signs and add. So I get 7x minus 4. Okay. Do you see how this 7x, it has a lower degree than this? That's when you know to stop. So, this is now equal to negative 2 plus 7x minus 4 over x squared minus 2x. Now, you're going to take this and you're going to decompose this. This, the one I... Huh? Oh, just 1x. Okay? All right, so let's decompose that. So 7x minus 4 over x minus 1. You see how they're still linear factors? We get two factors. Let's write them down. Two numerators, a and b. We're going to multiply by x minus 1, x minus 1. Okay, 7x minus 4 is equal to a, x minus 1, plus b times x. So this is all like, so, you know, like these two steps now were more algebra 2, right? So we're going to move past. Okay, what are we going to plug in here? X equals 0, and I get negative 4 equal to negative a plus b times 0. So a is 4. What else did you say? 1. 7 minus 4 is 3, equal to a times 0 plus b times 1. b is 3. Now, my initial fraction was this. Negative 2x squared plus 9x minus 4 all over x squared minus x equal to. I decomposed this, I divided this, and I got negative 2 plus some other stuff. Most common mistake is people forget about the negative 2. No, you got to bring it back. Bring back the negative 2 plus the stuff that we just got, which is something over x plus something over x minus 1, and it's 4 and 3. Okay? So there you have it. Okay, so what if you did it in different order from the beginning? What if you're x minus 1 first, then x? Well, then the x minus 1 will have gotten the a, and the other one will have gotten the b. You will get 4 and 3 again, right? And magically, the variable that had the x will get the 4, and the variable that had the x minus 1 will get the 3. So no matter what, this will still end up in the same way. Okay, questions? Now for case 2. Case 2 is when the denominator has linear factors, but they're repeated with different, more like greater multiplicities. Okay, if the denominator has a linear factor that is repeated, you must include a partial fraction with its own constant numerator for each power 1 to n. Okay, that's a very confusing sentence. But let's take a look. Look at this denominator here. You've got an x cubed. Okay? The exponent there is a 3. What's the base? X. Yeah? X cubed. Exponent is 3. The base is x. What's the exponent? 3. Whatever the exponent is, you have to clone that denominator that many times. So if there is 3 of them, you clone it 3 times. Okay, hang on. And then the exponents have to increase to this 3. So you start with 1, 2, 3. Okay? We're not going to ask why. We're just going to learn it for now. Okay? And don't think too much about it. But you build up the exponent to this number. The other one is x minus 1 to the power of 2. The base is x minus 1. The exponent is 2, so it repeats twice. And you build up the exponent 1, 2. Cool? Okay. Total degree here is 5. 3 plus 2 is 5. You should have that many fractions. Now, in the numerator, okay, you just go A, B, C, D, E, you know, however many times. You can go down to M if you want, okay, if you need, all right? Okay, so let's do this one. When you factor this, you get x x squared minus 4x plus 4. No, because you have 4x.
Never mind, sorry.
But we're going to factor that further. So we're going to have 3x squared minus 5x plus 4 all over x times x minus 2 squared. Okay, the x happens once. The x minus 2 happens twice. So you have an x minus 2 to the 1 and an x minus 2 to the 2. Okay, now, it doesn't matter what the exponent is in each of these. The thing that's being raised to an exponent is linear, correct? This is linear. Here, it's x cubed at the very top. Right here, you have an x cubed, but still, the thing that's being raised to the power is linear. That's why its numerator is a constant, 1 degree less. Okay? So here too, whoops, A, B, C. Okay, same as before. Let's multiply by the LCD. So I get 3x squared minus 5x plus 4 is A, x minus 2 squared plus B, x minus 2 times x plus C times x. Okay, so what should we plug in first? 0. I get 4 equal to 4a plus b times 0, c times 0. Fabulous. A is 1. Okay, what else should we plug in? 2. You get 6 equal to a times 0, b times 0 plus 2c. So c is 3. Okay, I still need b, right? I've exhausted all of the values of x that will make the factor 0, but you know what? I can still plug in whatever number I want. The reason why I was plugging in the ones to make it 0 was to make things simpler for me. So, I mean, I could still plug in like 153.7 if I want, right? But we're not. We're going to plug in x equals 1. Okay? Because that's my favorite number after 0 to plug into things. So here I get 2 equal to a times negative 1 squared plus b times negative 1 plus c. Okay, so what we get here is 2 is a minus b plus c. Technically, this is why this is in the matrices chapter. Because if you plugged in random numbers for each of them, then you would have gotten 3 equations and 3 unknowns, and you would have solved it using a matrix. But we're not going to do that. It's not necessary. But here, we know what A and C are, right? You just plug them in. So B is equal to 2. That means that complicated fraction is equal to, what did we have? So x minus 2, x minus 2 squared, and we had a, b, c, right? So 1 and 2 and 3. Ha! 1, 2, 3. Also a coincidence, Ben. Okay. All right. Last but not least, a denominator. Okay, I'll give you a minute. This is case 3. When you have a denominator with prime quadratic factors. So a quadratic factor that cannot be factored. In this case, if you have a prime quadratic factor, then you must include a partial fraction with a linear numerator like bx plus c. Okay, what do we mean by that? Take a look at this one. The denominator is factored all it can be factored, right? That x squared plus 1 is quadratic, and it cannot be factored anymore. So, okay, fine. So now we have two fractions, one with the x squared plus 1. So notice the difference of this compared to this. Do you see how this is quadratic? X minus 1 just has an exponent. This one is linear, not quadratic. This one linear, just has an exponent. This one is quadratic no matter what you do. Well, remember what we also said, that the numerator has to have 1 degree less? Well, here if you have an x for the denominator, then 1 degree less would be a constant, so you have an a. But here, if you have a quadratic, 1 degree less would be a linear function. And what's our favorite form of a linear function? Y equals mx plus b, right? What's mx plus b? Some constant, x plus another constant. Well, why is it mx plus b? Why isn't it ax plus b? Why isn't it bx plus c? Right? It could be anything you want. So, if you use a here, then this is going to be bx plus c. Okay? Or if you had used them all, it would have been like ex plus f or whatever. Okay? All right, so let's do this next one. I have x cubed minus x over x squared minus 3 squared equal to, okay, two fractions here. One with x squared minus 3 and one with x squared minus 3 squared. Numerator, I have ax plus b, and you tell me. Fabulous. Okay. Okay, so this isn't really good form, but I'm just going to do it. We're going to multiply everything by x squared minus 3 squared. Okay. So I get x cubed minus x equal to ax plus b in parentheses times x squared minus 3 plus cx plus d. Okay, this one's a little different, but fun. I love this. This is my favorite case of all of them. Okay, so we're going to multiply these out. Okay, so this is ax cubed minus 3ax plus bx squared minus 3b. Okay, plus cx plus d. Okay, now here's what we're going to do. At this step, we're going to group these by degrees of x. And the reason why I love this is because we do some mathematical tricks that you've never done before and that we don't get to do all too often, but it's so much fun. So here's what we're going to do. X cubed minus x equal to, okay, so this is ax cubed, okay? Now write all of the x cubes together, all of the x squared, so just rearrange them. So plus bx squared, and then minus 3ax plus cx minus 3b plus d. Right, so I have done no math here. I just rearranged. Now, what you're going to do is you're going to factor, okay, by the degrees of x. Okay, so, yep. So then factor. So we're going to factor by degrees of x. Here's how that works. You have x cubed minus x equal to ax cubed. That term's alone, right? There is no other x cubes. The bx squared is alone too. The x squared, there's only one x squared term. Now look here. Do you see how both of these have an x term? You're going to factor out the x. So you're going to get plus, in parentheses, negative 3a plus c times x. Cool? Yeah? And then plus, this is another term. It's all constants. I'm going to lump them together. Okay, now, you know what you're going to do? So look at what you have here. You have some x cubed term, x squared, x, and a constant. On the left side, you have some x cubed term, an x term, and you can have some other things. What you're going to do is you're going to compare the coefficients of the like terms and set them equal to each other. So compare coefficients of like terms and set equal to each other. Okay, what do I mean by that? Take a look on the right-hand side. You see the ax cubed? You see the x cubed term? Where is the x cubed term here? There. Okay, on the left, what's the coefficient of the x cubed term? 1. So if those are equal to each other, their coefficients should be equal to each other. So 1 equals, what's the coefficient here? A. Oh, look, a equals 1. Next, you can do that. You can do that. Here, x squared. What's the x squared here? 0. So the coefficient of there is an x squared term, it's just that the coefficient is 0. It's 0x squared. So the coefficient here of the x squared is 0. Here it's b. So I can just say 0 equals b.
That's crazy.
I know.
Wait, you can just do that? This is just fun.
They're equal equations.
I think there's a 1.
Is there an x squared term here? So the coefficient was 0. It's 0x squared.
Okay.
Yeah?
Oh, okay.
Okay. Next. This is the x term. What's the coefficient?
X, 1.
Okay. On the left-hand side, the coefficient is -1. On the right-hand side, yep. So -1. What happened here? -1 equals -3a plus c. Okay? So this is -1 equal to -3 times 1 plus c. C is equal to 2. Again, you see how like matrices could have come in handy?
I'm okay now.
And then last but not least, this is the constant term. What's the constant term on the left side of the equation? 0. So -3b plus d is equal to 0. -3 times 0 plus d is equal to 0. Lo and behold, d is 0.
That was fun.
So now, okay, the function is, well, initially, we had this equal to, we had x squared minus 3 for one, and then x squared minus 3 squared for the other. And we had ax plus b, right? Well, ax plus b is what? 1x plus 0, and then 2x plus 0 for cx plus d. And of course, we're not going to write it like that. So we're just going to say this is equal to x over x squared minus 3, 2x over that thing squared. Okay? And there you have it. Okay? That is fantastic.
I love your